Welcome to today's paper reading. Today's paper is titled, Chain of Table, Evolving Tables in the Reasoning Chain for Table Understanding. This paper, published at Eisenschlos 2024, presents Chain of Table by Zilong, Wang and colleagues from the University of California, San Diego and Google. The abstract introduces table-based reasoning with large language models, LLMs, emphasizing the need for extracting underlying semantics from both free-form questions and semi-structured tabular data. This approach is crucial for tasks like table-based question answering and fact verification. The authors proposed the Chain-of Table framework, which explicitly incorporates tabular data into the reasoning chain. This framework guides LLMs through in-context learning to generate and update operations iteratively, allowing for dynamic planning based on previous results. The continuous evolution of the table forms a chain that visually represents the reasoning process. This structured approach leads to more accurate and reliable predictions. The Chain-of Table framework has achieved new state-of-the-art performance on benchmarks including Miculicich, Fujii, and TabFact across multiple LLM choices. Tables are a prevalent data format, utilized extensively in everyday life, providing rich information through their structured interactions of rows and columns. This structure enhances data capacity but complicates understanding for language models. Reasoning over tabular data is crucial in natural language processing, attracting growing attention. To address this, the authors propose Chain-of Table, a method that conducts step-by-step reasoning through tabular operations, transforming tables to store intermediate results, thereby improving table understanding. Figure 1 illustrates the differences in reasoning methods for complex tables. Generic reasoning, A, fails to provide correct answers due to the complexity of the table structure. Program-aided reasoning, B, generates and executes programs like SQL queries but struggles with accurately parsing the name and nationality within the table cells. In contrast, the proposed Chain-of Table, C, iteratively samples a series of operations that effectively transform the complex table into a version tailored specifically to the question. This method allows the LLM to arrive at the correct answer by dynamically adjusting the table structure to fit the reasoning needs. In the realm of table understanding, several approaches have been developed to fine-tune language models. Tomas, for instance, reconstructs certain cells in tables during pre-training, while Pfister and Tutor mask entire columns or segments. Tapex takes a different approach by pre-training an encoder-decoder model with a synthetic SQL dataset to act as a SQL executor. On the prompting side, Chain of Thought, COT, and its successors like Tomas and Decomp generate reasoning steps before answering, enhancing the model's ability to solve complex problems. Jean and Liu further enhance COT with a table-filling procedure. Researchers also leverage external tools, such as generating Python programs for reasoning tasks, which significantly improves arithmetic reasoning. Text-to-SQL with LLMs is a direct application of this idea, and binder and lever extend program capabilities by verifying generated programs. However, these methods often struggle with complex tables due to the limitations of single-pass generation. Our approach, Chain-of Table, addresses these limitations by conducting multi-step reasoning and transforming tables dynamically. In table-based reasoning, each entry is represented as a triplet, T, Q, A, where T is the table, Q is a question or statement, and A is the expected answer. The objective is to predict the answer A given the question Q and the table T. The Chain-of Table framework enables LLMs to dynamically plan a chain of operations over a table in response to a given question. This framework utilizes atomic tool-based operations such as adding columns, selecting rows or columns, grouping, and sorting. The process involves iterative sampling of operations, generating arguments for these operations, and finally querying the LLM to predict the answer based on the transformed table. The experiments evaluate the Chain-of Table method on 3 public table understanding benchmarks, Miculicich, Fujii, and TabFact. These datasets require complex tabular reasoning to answer questions or verify facts. The evaluation metrics vary by dataset: denotation accuracy for Miculicich, binary classification for TabFact, and BLEU and Rouge scores for Fujii. The experiments utilized 3 large language models as backbones: PaLM 2S1, GPT 3.5, and Llama 2. In-context learning is performed using few-shot demo samples from the training set, with details provided in Appendix C. Table 1 presents the results of table understanding tasks on the WikiTQ and TabFact benchmarks using 3 different language models, Palm 2, GPT 3.5, and Llama 2. The table highlights that the Chain-OF table method significantly outperforms all other generic reasoning and program-aided reasoning methods on both TabFact and WikiTQ. The performance is evaluated using binary classification accuracy for TabFact and denotation accuracy for WikiTQ. Notably, Chain-OF table shows substantial improvements over the second-best performing methods across all 3 language models, indicating its robust and superior performance in table understanding tasks. Table 2 presents the distribution of the number of samples versus the required length of the operation chain in Chain-OF table with Palm 2 on the WikiTQ and TabFact datasets. The data reveals that the majority of samples need between 2 to 4 operations to generate the final output. This observation underscores the efficiency and effectiveness of Chain-OF table in handling tabular reasoning tasks, particularly when compared to other methods that may require more operations or struggle with larger datasets. Figure 3 illustrates the performance of chain of thought data and the proposed Chain-OF table on WikiTQ for questions requiring varying lengths of operation chains. The proposed Chain-OF table method employs atomic operations that enable dynamic transformation of input tables through multiple reasoning iterations, significantly enhancing performance compared to generic and program-aided reasoning methods. Table 3 presents the performance metrics of binder, data, and the newly proposed Chain-OF table method across different table sizes from the WikiTQ dataset. The results indicate a general trend where larger tables lead to decreased performance for all methods. However, Chain-OF table demonstrates a more controlled performance drop compared to the other methods, maintaining its effectiveness even with larger inputs. This resilience is highlighted by its significant improvements over both binder and data, particularly in handling large tables, where it achieves over 10% better performance than the second-best method. This suggests that Chain-OF table's approach to table reasoning is particularly adept at managing the complexity and length of larger datasets. Table 4 compares the number of samples generated by binder, data, and Chain-OF table for a single question on the WikiTQ dataset. Chain-OF table stands out by generating the fewest samples, significantly less than both binder and data. Specifically, Chain-OF table generates up to 25 samples, which is 50% fewer than binder's 50 samples and 75% fewer than data's 100 samples. This efficiency is crucial for reducing computational overhead and improving the speed of question answering processes. Figure 4 illustrates the tabular reasoning process within Chain-OF table. This process is iterative, involving the dynamic planning of an operation chain and the accurate storage of intermediate results in transformed tables. These intermediate tables act as a tabular thought process, guiding the LLM to reliably reach the correct answer. The Chain-OF table method significantly enhances the reasoning capabilities of large language models, LLMs, by utilizing a tabular structure to express intermediate thoughts during table-based reasoning tasks. This approach instructs LLMs to dynamically plan an operation chain according to the input table and the associated question, which represents a novel advancement in prompting LLMs for table understanding. Additionally, the reproducibility of this research is ensured through the inclusion of prompt examples in the appendix, the use of official open-source code, and the revision of the code to accommodate publicly available models such as GPT 3.5, Palm 2, and Llama 2. Thank you for watching.